All right. Last time we talked about the linear equation, which I wrote here, and basically the linear principle guarantees that we can write the general solution to be a decomposition of a particular solution plus the general solution of the homogeneous case. All right. So now this time we want to actually go ahead and try to solve this differential equation. So how do we solve it? Basically the idea is here. What we want to do is we want to, let's just write down ideas. It's a very simple idea. After that, we show two examples, and then this part should be easy. We just put this one here, okay, and remove everything to the other side. And for simplicity, we can deal with negative, but we can change it to be positive by slightly changing your AT to be a GT. Okay, which is fine. And then what we can do is we can think about this part. We have a derivative. Therefore, to find y, we want to take the integration. So our final goal is going to take integration. Okay, probably with respect to dt, which is fine. But now, if we take an investigation on this thing, the right-hand side is pretty easy because it's a function of t. If you just take the integration, you just take the integration with respect to dt. Okay. The part you have trouble is actually how do you do this? Because this is not something easy to take integrations with. Okay? Now, basically what we want to do is if we can find the antiderivative of this, it's all set, then it will be best if somehow what we see here is actually the derivative of something. If we could find such thing, the whole thing will work. Okay, let me think about it again. Basically, we need everything on the left-hand side. Whatever gt you put in can be just the derivative of something. Okay, with respect to t. If that happens, if you take the integration, you simply just have the antiderivative already. Of course, this won't happen in general. Okay, but now we will try to make it happen. How do we do that? Let's take a look at this. Forget about gt. What I see here is y prime and a y and a plus. That means in one part, this one was taking the derivative. In the other part, it is not taking the derivative. And then you sum them together. Try to recall what you had in calculus. Which kind of derivatives give you this kind of properties? You have two terms. The first one, you take the derivative. The second one, you don't take the derivative for one term. It may take a while, but eventually, maybe we can realize this is product rule, right? Let's write down product rule. What do you have for product rule? What you have for product rule is if you have f and a g, okay, or let's use f and y, okay, and if you take the derivative, you are going to have f prime times y plus, let's change the order. You are going to have f y prime plus f prime y, which is exactly y prime and y, and then take the sum. So what you're hoping is you can find an f such that this one here is your f and this one gt here is your f prime. That's what you're hoping. Okay, and of course in general this won't happen, but now what we will do is we will try to make this f such that the whole thing works. Okay. And let's just take f to be, oh, actually, let's stay consistent. Let's use mu, because the book used mu, but the idea are the same. Okay, so make a mu. Okay, so think about this. What you have here is if mu y a mu t times y is going to be mu y prime plus mu prime y, then all you're trying to say is this should match this. Somehow you want them to be the same, okay, or connected. Then the first thing you want to do is probably you want to times this one, both sides by a mu. So you're going to have, you want this to happen, right? But this, if you times a mu on both sides, you are going to have a mu t, y prime, that's what you want, plus gt times mu t times y. Now these two look very similar. The first term is the same. The second term will be the same if this part equal to this part. Okay, so how do you do that? Well, you just solve this. Can you find a mu such that this happen? And you found number one, this is the homogeneous case. Okay, you know how to do it. Second, actually it's super easy because you have mu prime, mu t, okay, equals gt because it's separable. Therefore, you can actually get this mu. That is ln mu t equals gt. We don't know what this function is. It depends on g, but it's solvable. Then your mu is going to be e integration gt dt. You may have a plus times c here. You may have some positive or negative here, but really, we just need one that will work. So this will work. Okay. So let's go back and think about what we just did. We started from y prime plus gty equals bt. That's where we started. Okay. Now we say, hey, the one on the left, we want to do the integration. Therefore, we're hoping it's coming from some perfect derivative. And we find that is going to be a product rule. It should come from here. Which is mu prime, mu y prime plus mu prime y. Okay, this will give you that if you could make this one. Okay, but then in order to do that, you need to times everything by mu. Therefore, the one in the middle, if you want to make this happen, you have to make this happen. Therefore, we have a differential equation to solve to find a mu such that it satisfies these two are the same. Which means if you multiply a mu like this, it is guaranteed it comes from a perfect product rule. And the additional trouble you have is if you times a mu on the left-hand side, you have to times a mu on the other side. The good news is mu is a function of t. So even if you times it on the other side with a bt, it just makes the whole function of t more complicated, but still it's doable because it's just a function of t. So finally you have this. And finally you can take the integration on both sides. You will have ut y equals the integration of mu t bt dt, and you can just continue. Okay, and solve it. When you finish, divide ut on the other side. So that's roughly the idea. We went over every idea really quickly. The logic is clear, but it may take you several times to let it sink in. Since we're shooting a video, so you can pause and rewatch to make sure you understand the process here. But now if I need to summarize all the steps, it becomes easy. So when you see something like that, let's ignore every thinking process we have and just focus on the mechanics. The first thing you want to do is you want to multiply a mu on both sides. And which mu should you multiply? The mu should be the one solves that differential equation. So it's going to be this. That's step one. Step two, once you finish that, there is a guarantee this one is going to be mu times y prime. And then the next step is try to take the integration. You got mu times y. And take the integration on the other side, you have mu t bt. Whatever integration you get from there, finish after that. So the key is you need to multiply a factor on both sides to make this work. This is called the integrating factor. integrating factor. So that's the point of doing this whole section. Okay, let's try several examples. See how we do this. Number one, we have y prime plus 2 over t times y equals t minus 1. Now the first thing is we want to calculate mu. Mu is e to the integration 2t dt. You put your gt here. Now do the integration is going to be to e to the ln t 2, which is t squared. So that is going to be my integrating factor. Then what I want to do is I want to take this one and times t squared on both sides. All right, this part become 2 times t. Now you can clearly see this is going to be t squared y prime. To check your work, you simply just take the derivative. You have 2t y prime plus, t squared part y prime plus 2t, which is the derivative of t squared, times y. So magically, after you multiply the integrating factor, this one becomes the derivative of this one, so you have a perfect product rule. But of course, we know this is not magic. We actually backtracked everything in order to find for which mu. The way we compute mu will actually guarantee this will happen. So the left-hand side becomes this. The right-hand side is what it is. Now you can take the integration. The integration of the derivative is just itself. And the integration of this one become more complicated, but still it's just a function of t, so you can do it. Plus a c. Therefore, your y is going to be 1/4 t squared minus 1/3 t plus c over t squared. That is the method of numerical integration. Integrating factor. And this is the integrating factor. The way to compute it is just put gt here in this format. Once you finish, you're guaranteed to have a product rule. It's not too much trouble to actually check your work. So make sure that every time you go here, check your work by taking the derivative really quickly to make sure that you have multiplied the correct numerical integrator. Integrating factor. I keep saying that. Okay. If that's the case, this is nice. Let's try another example. We have y prime equals negative y 1 plus d plus t squared. So again, step 1, change everything into the standard form to move the y term on here. To see more clearly, you can actually separate the t part and the y. Okay. Now numerical integrator. Integrating factor. Okay, then times 1 plus t. Cancel. Now check, do you have the derivative of this is actually the derivative here, which is 1? The answer is yes. Therefore, we do have a product rule. The next thing is just try to do the integral. Plus a c, so y equals, if we don't want to simplify, we can simply just keep things in this way. That's it. All right, that's basically the idea of doing integrating factor. To try to multiply a term such that the one on the left will become a perfect product rule. And then when you have a perfect product rule, when you take the antiderivative, it's going to be easy to find the integration. The drawback is the right-hand side originally was bt. Now if you multiply mu t, you get a mu t times bt. which will make the original function more complicated usually, but it's no big deal because it's still an integration with respect to t. You don't have those kind of difficulties when you have y and t together, so you don't know how to take the antiderivative. All right, now final example, the one we said before at the beginning. We were trying to do a application of linear equations. Now we can do it. What we can do is we can take y to be your long, remember, and we have interest rate. I think it's 1% per month. So it's a monthly rate, and you have a monthly payment. $700. Now we set up a differential equation. We said, okay, for every month, your loan is going to increase due to the interest times your current value, but then you are going to make a payment, which is minus 700. And clearly this one become a linear differential equation. Now we can actually go ahead and solve it. This is minus. All right. Now numerical integrator. Integrating factor. The whole thing here is actually your gt, including the minus. And there's no t, so it's just a constant, which is e to the... Okay. Is that... All right, now check the left-hand side. You should have this. Do you? Well, if you take the derivative, you keep this part, take y prime, you got the first term. Now if you keep the y term and take the derivative of e to the negative 0.01t, you got exactly this, including the negative sign. From here you can see, well, it worked. It's a perfect product rule. And because of that, we can now solve it. And now the negative thing is gone. If you feel kind of shaky, try to verify by taking the derivative. You can see it is the answer. So finally, your y is going to be minus, oh, there is a plus c, 7 plus c e negative 0.01 t. This is the plus because you are dividing. All right. So basically what you're going to get is you are going to get a final answer like this. It may looks not intuitive. The reason is because you have some 70,000 and you have a plus c, and this part is clearly growing, exponential growth. So maybe you're trying to see like, okay, my loan is going to increase exponentially no matter what. Well, even though everything looks like so, but if you just try to assign it, for example, let's take y0 equals 200,000. Even if you just take an initial value and try to see what's going on, then what you have is plus a c equals, when this one is 0. So the whole thing here is actually 1 if you plug in t equals 0. What you can have here is c equals where I have this, which is positive. So in that case, actually, if you just have an interest rate like this monthly and you're paying $700, you will never be able to repay your debt. Yes, your debt just grows exponentially, for sure. But if your initial condition is actually small, let's take y0, it's going to be 50,000. Okay, then you can actually have 70,000 e, plug in 0, so this is gone, plus c equals 50,000, and your C is actually negative 20,000. In that way, your final answer is going to be y equals 70,000 plus C, which is minus. So from here, you can see actually when you have exponential growth, you are going to have a negative number in the front. So you are going to pay your debts. Your loan is going to decrease quicker and quicker and quicker because you have exponential growth on the minus part. So really, even this one actually seems like it's going to grow forever, but really you should ask, like, is my C positive or negative? Seems like if you have a 1% monthly rate, it seems like if you have a monthly payment to be 700, for anything below 70,000, you can actually pay it. Maybe it will take a long time, but you can actually pay it. But if it goes beyond that, your monthly payment will not be able to cover your monthly interest. Therefore, you would never, there will be never any money going into your principal. Therefore, you will never be able to repay the debt. Okay, so that's a classic application of linear equations, and the way to solve it is integrating factor. Great. So that's everything we need to know about first order differential equations. Next, we will move to linear systems. Not linear systems yet. We will move to first order systems. Okay.